Hi everyone. Today we are very happy to have Onkar Parrikar from Stanford telling us about his recent paper on modular Hamiltonians for Euclidean path integral states. As usual, please feel free to interrupt with questions if you have them, and we'll try to make this interactive and give some feedback to Onkar. Go ahead.
Thank you. Thank you so much for the invitation to speak. It's such a pleasure. And please, again, as you said, please feel free to ask questions along the way. So this talk is about this particular paper, which came out earlier this year with Srivatsan Balkrishnan, who is a graduate student at Urbana-Champaign. Okay, so we all know that modular flow has many interesting applications. Just to list a few, for example, it has been used in deriving energy conditions of various types in quantum field theories. In ADS-CFT, for example, the generalized Ryu-Takanagi formula tells us that the boundary modular flow equals bulk modular flow. And you can use that statement for bulk reconstruction and various other purposes. And you can also argue that this equality of bulk and boundary modular flows conversely sort of implies the Ryu-Takanagi formula. So given all of this, given this list, we sort of, it's useful to study modular flow in quantum field theory in some generality. But unfortunately, the way it stands right now, the sort of modular flow is well understood by and large for symmetric subregions in special states. So for example, half spaces or ball-shaped regions in the vacuum state of conformal field theories. In this case, modular flow is quite well understood. But beyond that, it's somewhat hard to deal with either in excited states or even in the vacuum. If one considers non-symmetric subregions, then it's not very easy to keep a sort of control modular flow. And so our goal in this talk is going to be to make some progress in this direction. So just so that we are all on the same page, let me just start by giving some definitions. So let psi be some general state in a quantum field theory. Typically, we define these states on Cauchy slices. So let's sigma be this Cauchy slice. So in this cartoon here, this slice here at t equals 0 is my Cauchy slice. And then we pick some subregion, which is the shaded region, which I will call R inside the Cauchy slice. Now, if you assume that the Hilbert space of your CFT, or more generally your quantum field theory, factorizes between R and R complement, then you could imagine tracing out the degrees of freedom in R complement and constructing the reduced density matrix for your state inside the subregion R. Now, of course, more generally in quantum field theories, this factorization argument is not valid, but we'll see that for our purposes, it would be sufficient to just assume this, although more or less some of the results that we'll present are likely to generalize even beyond that. But so anyway, if you construct this density matrix, which is obtained by sort of tracing out the degrees of freedom in our complement, then you can define the entanglement entropy of this density matrix or of the subregion R as the von Neumann entropy of the reduced density matrix. Okay. So if you like, the entanglement entropy is some measure of how much quantum entanglement there is between the subregion R and its complement. Now, the entanglement entropy is just one number, but there is, of course, much more fine-grained information in the full density matrix. So there's a lot of information about the structure of entanglement, if you like, contained in the density matrix. And in simple cases, you can construct this density matrix pretty explicitly using Euclidean path integrals. So just to remind you of how this works, let's consider a simple example, namely the state we will consider is the vacuum state, and the subregion that is of interest will be sort of a half space. So imagine that x1 is some coordinate, some spatial coordinate. We just consider a subregion R, which is x1 greater than 0. And then there could be some transverse coordinates, which I'm not drawing in this figure. So in very generally, the vacuum state of a quantum field theory can be constructed by performing the Euclidean path integral on the lower half space. So imagine that this vertical direction here is the Euclidean time. And we perform the path integral, the Euclidean path integral for Euclidean time less than 0 that prepares for us the vacuum state of the field theory on this Cauchy slice at t equals 0. Now that's the ket. The bra is similarly constructed by performing the time reverse of this path integral on the upper half space. And then if you want to construct the density matrix, you have to trace out our complement. That is achieved by gluing these two path integrals together along our complement over here. Okay, and so what that gives you is this Euclidean path integral on the full Euclidean space, but with a cut along your subregion R, here denoted with this cut shown in blue. Okay, so that would be a Euclidean path integral construction for the density matrix in the vacuum state. Now, a convenient way of characterizing some of this information contained in the full density matrix is to define what we call the modular Hamiltonian, which is defined as minus the log of the density matrix. So roughly the idea is to think of the density matrix as some thermal ensemble with some Hamiltonian, and that Hamiltonian is the modular Hamiltonian. Now, it's sometimes also more useful to define what you might call the full modular Hamiltonian, which I'll denote here with a hat, which is basically the modular Hamiltonian of the subregion R minus the modular Hamiltonian of the subregion R complement. Okay. The reason to do this is that one way to see why this is a more useful operator is that the modular Hamiltonian by itself may have some UV divergences associated with it near the entanglement cut. And the difference of these two does not have, I mean, the divergences close to the entanglement cut cancel out between these two. And one expects to find a regular operator near the entanglement cut. Now, it's very easy to check that this full modular Hamiltonian annihilates the state psi with respect to which the reduced density matrix and so on is defined. And in some sense, this full modular Hamiltonian generates a symmetry of correlation functions in the state psi. Okay. Moreover, you can also define, so now we come to what we would mean by modular flow. So if you have any local operator O in the subalgebra of operators associated with R, so think of any operator contained inside, for example, the causal diamond of R, then one can define the modular flow of that operator by simply, if you like, time evolving that operator with this full modular Hamiltonian. Okay, so this is what we mean by modular flow. And the nice thing about this definition is that this modular flow does not move operators out of the algebra. So for example, if you start with an operator in the causal diamond of R, this modular flow operator will also stay within the causal diamond of R. Okay, if you assume Hilbert space factorization, that's sort of a trivial statement. But even without assuming the factorization of the Hilbert space, there is a very formal theory of often called Tomita-Takasaki theory, which basically ends up proving the statement that modular flow leaves you within the subalgebra. Okay, and so in some sense, you can think of this modular flow as a notion of time translation, which is intrinsic to the subregion R. Okay. So are there any questions so far? All right, very good. So then let's consider a simple example. If all of that seemed very abstract, we can see how some of this works in a simple example, namely that of the vacuum state, and the subregion of interest will be the Rindler wedge. Okay, so we already discussed that the reduced density matrix for the vacuum state is given by this Euclidean path integral with a cut along the subregion R. Now, if you want to take, so what we want to do is we want to take this path integral and interpret it as being a thermal ensemble with respect to some Hamiltonian. And the way to do that is you take this path integral and then you slice it open along these radial slices, or angular slices rather. And a little bit of thought shows that what this path integral is it's essentially generated by Euclidean evolution in this angular direction, where the sort of Hamiltonian in question is nothing but the rotation operator around this entanglement cut. Or if you want to think of it in Lorentzian, in the Lorentzian language, then this operator is nothing but the boost operator, which is here written in terms of the stress tensor. Okay, psi, this vector field psi is what would be the boost vector field in the Rindler wedge. Okay, so at least in the simple example of a half space in the vacuum state, we see that the modular Hamiltonian is just the boost operator, modular flow is a Lorentz boost, and it's nice and geometric. Of course, beyond this, if one considers non-symmetric subregions or excited states, then the modular Hamiltonian is not a nice local operator. The flow is not nice and local, but we'll see what happens to it. So that would be our goal. Our goal will be to study modular Hamiltonians in excited states. And the class of states that we are going to consider are the following. So we discussed already that the Euclidean path integral on the lower half space generates the vacuum state. Now, if you want to construct an excited state in this language, one way to do that is to simply turn on some source. So here in this cartoon, this gray blob denotes some region of the path integral where we've turned on a source, which I'm going to call lambda. And the source is turned on for some local operator, okay, which I'll call O of x. So we simply turn on a source in the Euclidean path integral for some local operator that will generate for you some excited state psi, and so our goal will be to study the modular Hamiltonian for such excited states. But we will only be able to do that perturbatively in lambda. So we'll take lambda to be small in some sense and expand in lambda. But the point would be to construct it to arbitrary orders. So we'll construct the modular Hamiltonian to any given order in lambda. Okay, as you all probably know, Euclidean path integral states are pretty directly relevant in ADS-CFT because they have geometric bulk duals. So it is, I would say, worthwhile trying to understand modular flow in this context. And as I already said, we are going to work perturbatively in lambda. And here are some references which have also dealt with this type of perturbation theory before. Okay, so here's the claim. The claim is that the modular Hamiltonian for this class of excited states to all orders in this source lambda takes this form. So K naught is the original modular Hamiltonian for the Rindler wedge. So I should say that the subregion I'm going to consider is always the Rindler wedge, but the state will be the excited state constructed with the Euclidean path integral with a source in it. So the claim is that the modular Hamiltonian is the original undeformed modular Hamiltonian plus an infinite series, where at the nth order in the series, you have a product of n of these operators O, where O is the same operator that we turned on in the Euclidean path integral. And these products, so this n local operator here is smeared with some smearing function over the Rindler wedge. Okay, so all of these operators are inserted inside this Rindler wedge, the original Rindler wedge, and they're smeared with some smearing function f sub n, which depends on the source lambda that we turned on. Okay, I'll tell you what these smearing functions are in the next slide, but before that, let me just remark that this formula is completely Lorentzian. In other words, these operators here, O's, are all inserted in the Lorentzian section in the Rindler wedge, despite the fact that the state was created using the Euclidean path integral. Okay, so that's one of the nice features of this formula, which is that it's manifestly Lorentzian. And these smearing functions f sub n, to tell you what the smearing functions are, I have to introduce some notation. So here's the gray shaded region here is the Rindler wedge. The plane that you're seeing here, this transverse plane, is sort of the Euclidean plane. So the coordinates are marked out. The vertical direction along this plane is Euclidean time. The horizontal direction is x1, the spatial coordinate along which we partition. And the direction out of the plane, which is called x0 here, is real time. Now in this Rindler wedge, we can define sort of a Rindler time or a boost time, which I'll denote by S. And in addition, there is also a Euclidean angular time, if you like, a modular time in the Euclidean plane, which will be denoted by tau. And finally, these capital Y's will denote spatial coordinates, but only along the half space. Okay, these sort of remaining coordinates here in the Rindler wedge will be denoted by capital Y. All right, so now having introduced that notation, the smearing function f sub n, which remember is a function of n points in the Rindler wedge. Each point in the Rindler wedge is denoted by a modular time s1 and sort of a coordinate along this half space, which is capital Y, and so on. So this smearing function then is given by this expression where you take n powers of the source lambda. The source lambda, of course, is inserted in the Euclidean plane. So you take n of those, and then you multiply them by this particular function little f of n, which is written down here. It's just some function involving cinches, product of cinches. You take that, you sort of plug in the argument of this fn is sort of has these taus in it, the taus being the Euclidean locations of the sources, and then you perform the tau integral. So you perform all of the n tau integrals. So that's some sort of transform of this product of sources, and that's what gives you the smearing function over here. Okay, so that's the smearing function which appears in this expression for the modular Hamiltonian. Are there any questions about that?
I just had one question.
Sure.
So in the end, in your Lorentzian expression, and I guess in the previous slide,
Yeah.
so these O's, I guess I have to be careful about the ordering. I mean, these are generally not space-like separated.
That's right.
Is that right?
Yeah, so they're ordered as written here.
Okay.
There's no time ordering or anything like that. They're ordered as written, but the thing is that they're all in Lorentzian time. So any given ordering is not problematic.
Yeah. Okay.
Yeah. Any other question? Okay, very good. So then for the rest of the talk, I'll first briefly sketch a proof of the formula that I just showed you. And then towards the end, I'll discuss implications for ADS-CFT and future directions.
Okay. So, sorry, just a
Yeah, of course.
One more question about the time dependence. So, I mean, let's see, if I were thinking about a conventional Hamiltonian and I had sort of operators at different times multiplied together, I might kind of think of that as being a pathology or sort of, or maybe associated with closed time-like curves or something like that.
Okay.
Is it? I guess I'm wondering if it would be interesting to ask whether there are situations that avoid that. So it seems like in some of these simple situations you avoid that issue.
Right. That's an interesting question. So one thing I should say is that although the operators here appear sort of out of time order and so on, that the time in which they're sort of out of time order is the boost time. That's sort of the modular time associated with the original modular Hamiltonian. And so what this is saying is that the modular Hamiltonian for the excited state, if you rewrite it in terms of the modular Hamiltonian of the original undeformed state, then you encounter all of these out of time order, out of real time order expressions in the Rindler wedge. But you're right. I mean, it does seem like you get all these out of time order operators, and if you compute correlation functions of this modular Hamiltonian, you'll encounter out of time order correlation functions. But they're all completely well defined. In principle, you can compute them.
Yeah, sure. Okay.
I mean, I guess I should contrast this with situations where you encounter out of Euclidean time ordering. In those situations, those operators are not well defined because their correlation functions diverge. But for Lorentzian out of time order operators, that does not happen. So that's a nice feature here. Okay, great. Right. So, all right. So let's begin by sort of briefly sketching a proof of this formula. I won't go into the gory details of it, but I'll just sort of give you a sketch of how things work. So the first task, of course, is to construct the reduced density matrix for the class of excited states that we are interested in. As I said, the excited state is built from the Euclidean path integral, but by turning on some source in the Euclidean path integral. So the density matrix, as before, will be constructed by taking the ket and the bra and then gluing them together along our complement. And so that's the density matrix is denoted by this Euclidean path integral here, where with some abuse of notation, I'm going to just denote this lambda with the full source now. So lambda consists of this time reflection symmetric configuration of sources in this full path integral. Okay. Now, once you have this expression for the density matrix, you can start expanding in powers of lambda. So for example, the nth order term in this expansion will pull down inside the path integral n powers of this operator O integrated against the source. So for example, here in this cartoon, I'm showing the fourth order term in this expansion, and there are four operators that have been pulled down inside the Euclidean path integral. Now, just like we did before, you can try to get some kind of operator expression for this density matrix by slicing this path integral along this angular direction. Okay, this is the same trick that we played before in the case of the vacuum state. And if you do that and think about it a little bit, then what you end up concluding is that the nth order term in this expansion basically has a time ordered product of n operators, where by time ordering here, I mean that you're sort of time ordering in this angular direction. Okay, this is the Euclidean modular time associated with the undeformed Rindler wedge. And it is in that time that you're time ordering. Okay, so think of each of these operators here as being Heisenberg operators defined like so, where you're sort of Heisenberg evolving in this angular time with respect to the vacuum modular Hamiltonian. Okay, so the nth order term in the density matrix will have a Euclidean time ordered product of n of these operators integrated against the corresponding sources. Okay, so now we have a nice expression for the density matrix, and the aim is to compute now the log of the density matrix. Very good. So the way to do that is the following. So we are going to use the following general result. If you have any matrix rho of lambda, then the derivative of, and let's say k of lambda is minus log of rho of lambda, then the derivative of this log, the derivative of k, is given by this particular integral expression. Okay, this is just generally true of any sort of one parameter family of matrices, if you like. Okay. Notice that this expression involves sort of this flow or modular flow, if you like, with respect to k of lambda. And the flow parameter is integrated with some kernel. So let me just quickly tell you how this formula is derived. Oh, I should have mentioned that this delta here is a derivative with respect to lambda, where lambda we are thinking of as just some parameter which appears in these matrices. So the way to derive this formula is the following. So whenever you take the log of a matrix, you have to be careful, because you see the derivative is defined by this first line over here. But the point is that inside the log, the rho and delta rho needn't commute with each other. So one has to be careful in taking the derivative. One way of doing that is you rewrite this first term here by pulling out this rho of lambda and writing that as like log of rho times 1 plus rho inverse 0. You can then interpret this expression, at least to the order that we are working in, as this rho of lambda is nothing but e to the minus k lambda, and and this term here, this remainder, is just e to the rho inverse 0. So now you have a product of two exponentials inside the log. So at this stage, you use Baker-Campbell-Hausdorff. So basically, one multiplies these two exponentials using Baker-Campbell-Hausdorff, and that gives, for the derivative of the log, this series involving nested commutators with the modular Hamiltonian. And these b's are Bernoulli numbers. And then one has to use an integral representation for these Bernoulli numbers. If you use this particular representation, then that allows you to resum the series in the form of this particular integral over the modular time. But note that this formula is just true at any value of lambda. I didn't set lambda to 0 anywhere, so this formula is just true at any sort of anywhere along the one parameter flow of these matrices. Okay, so this is the formula that we are going to use to successively compute higher and higher derivatives of the modular Hamiltonian. This is what I just said. Okay, so let's see how this works at first order. For example, at first order, I can simply just take this formula and I can set lambda to 0. Okay, so the aim is to compute this sort of perturbative expansion of the modular Hamiltonian. If I want the nth order term in this expansion, I simply take n-1 derivatives of this formula, and then I set lambda to 0. Okay, Of course, at first order, this formula already tells me what the derivative is. So I can just take this object, I can set lambda to 0 and evaluate it. Okay, so if I take this formula, I set lambda to 0, this is what I get. Now, the rho inverse d rho here has already been computed. Let me remind you that we over here, we had a formula for all possible derivatives of this density matrix. So we know what rho inverse d rho is. So in this particular case, that's given by this expression. This is simply the first order version of the formula that I showed you. So all we have to do is take this formula for rho inverse d rho, plug it in here, and then simplify. Note that this sort of modular flow, if you like, the Lorentzian modular flow that appears in this formula, sort of combines with the Euclidean modular flow that appeared in the first derivative of the density matrix. In particular, the s here just gets shifted by I tau when you plug this formula back in here. And then it's a simple matter of deforming the S contour, the contour of integration of this S variable in the complex S plane to get rid of all of that tau dependence from within the operator so that all of the tau dependence gets removed from the operator and it sort of gets shifted inside this kernel, this smearing, this function here, which appeared out front. And so what you're left with is, if you think about this expression a little bit, what this is essentially the operator now is essentially entirely inserted in the Lorentzian in Lorentzian time, in the Rindler wedge in particular, and then there's a smearing function shown over here, which sort of combines the source and this sinh square down here, and you perform the tau integral, and that gives you the smearing function. Okay, so simply by doing this contour deformation, what we've managed to do is we've managed to rewrite the first derivative of the modular Hamiltonian as a manifestly Lorentzian operator, which is nevertheless smeared with some smearing function. Okay, are there any questions about that? Okay, very good. So now that was the first order result. Things get a little bit more complicated at higher orders. So for example, let's consider the second order expansion. Now here I need to compute the second derivative of the modular Hamiltonian. Well, how do I do that? The first derivative is given by this. If I want the second derivative, I just take another derivative of this object with lambda and then set lambda to 0. So that's this expression. Now, this derivative can either hit this first exponential, or it can hit this rho inverse 0, or it can hit this second exponential. And so that's going to give you a sum of 3 terms. Now, each of these 3 terms can be evaluated explicitly. If the derivative hits the first exponential, that can potentially pull down like the first derivative of the modular Hamiltonian, but we already worked that out in this slide. So we know what the first derivative of the modular Hamiltonian is. If the derivative hits the rho inverse 0, then we are good because we already know all of the possible derivatives of the density matrix. And similarly, this last term can also be evaluated. Okay, so all of these 3 terms can be explicitly evaluated. And in the intermediate stages of this calculation, you do find operators which are flowed in modular time. But somehow the magic is that you can still deform. There's a contour deformation of the S contour that one can do, where what happens is that all of the Euclidean Euclidean time-evolved operators coming from this first term and from the second term cancel out with the third term. So in other words, there's a somewhat surprising cancellation between these 3 different terms that you get in this expression. And when you, at the end of the day, what one is left with a purely Lorentzian operator. All of the operators which sort of had some Euclidean time evolution in them cancel out between these three different terms. And one is just left with this purely Lorentzian operator. Once again, these two are inserted in the Rindler wedge, and then there's some smearing function. And just similar to what we found before, this F2 smearing function now has two sources, and it's integrated along Euclidean times with this particular combination of centers sitting down here. Okay. And this is you can, so we worked iteratively in the number of derivatives, and we were able to show that at any given order in the derivative expansion, or in this perturbative expansion, this is exactly what happens. All of the Euclidean time dependence somehow cancels out between various terms, and one can always find a contour deformation which removes all of the Euclidean time dependence and gives you a manifestly Lorentzian operator. So this is how we ended up deriving this final formula that I had claimed before. And I guess I should remark at this stage that one of the fact that all of the Euclidean time dependence cancels out and you're left with a manifestly Lorentzian operator, that has the advantage that if you try to calculate any of sort of, if you like, relative entanglement entropies or any other information theoretic quantity with this Lorentzian expression, then they never encounter Euclidean time ordering problems. And so the things that you compute with this modular Hamiltonian are always finite and well-defined, which is what you would expect, and which is sort of a nice feature of working with this formula for the modular Hamiltonian. Okay, so are there any questions before we go on? All right, very good. So so having discussed a little bit how this formula comes about, let me now briefly tell you about a few applications that that we had in mind. So one application, which is rather straightforward, is to compute the modular Hamiltonian for a shape-deformed subregion. So even if you're in the vacuum state, as we discussed before, the sort of, if you consider regions which are not nice and symmetric, then the modular Hamiltonian is still complicated. One simple situation you could consider, however, is where the subregion is a slightly deformed half space, where this deformation vector field is denoted by V plus and V minus. These are sort of the null components of this vector field perpendicular to the entanglement cut. And X vector here denotes the coordinates along the entanglement cut. So then you can use this formula to deduce what the modular Hamiltonian is going to be for this deformed subregion. And you end up obtaining a formula involving sort of these half-sided null energy operators and higher powers of them integrated on the future horizon and the past horizon of the Rindler wedge. So here I've only shown up to the quadratic order in V. In the paper, we give the full expression to all orders. But generally speaking, you get terms like these. You get half-sided null energy operators and nested commutators thereof integrated on the future and past horizons of the Rindler wedge. Okay, so that's one application of this formula. Another more interesting application to my mind is to ADS-CFT. So we know from JLMS that the boundary CFT modular Hamiltonian should be equal to the bulk modular Hamiltonian plus this operator, which is localized on the Ryu-Takanagi surface, the area operator. And so bulk modular flow is equal to boundary modular flow and so on. But we now have a manifestly Lorentzian expression for the CFT modular Hamiltonian. And somehow that the expression we have should know about, or should already contain inside it the physics of the bulk modular Hamiltonian and the bulk area operator. So one interesting question that we are currently working on and would like to make further progress on is how to see this more explicitly. In other words, how to take our formula for the boundary modular Hamiltonian and rewrite it in the bulk in a way that this JLMS formula becomes manifest. So that's still work in progress, but I can show you how this works at least at first order. So at first order, the expression that we have is of this form. Once again, this operator O is smeared over the Rindler wedge with some smearing function. And now the objective would be to take this formula and rewrite this formula in a holographic CFT in bulk gravitational variables, where sort of the JLMS formula becomes manifest. And this was in some sense already done in this old paper in 2017 with these collaborators. The idea, although this was not exactly phrased in these terms, but the idea was that if you have some operator in the Rindler wedge, O here, then you can rewrite that operator as a bulk operator by using the bulk symplectic form. So what one does is one imagines that this operator O in the CFT is dual to some field, which I'm going to call phi. Phi is the bulk field which is dual to O. And actually, in this expression, phi is the HKLL operator that's dual to O in the bulk. And omega is the symplectic form density for this bulk scalar field phi. Okay, so in this formula, what one does is one takes the symplectic form density of the bulk scalar field. The symplectic form density is a two form in the field space or the space of field variations. So you have to feed it two objects. The second object here is the HKLL operator phi. And the first object is the retarded bulk to boundary two-point function, where the source point is this boundary location. And of course, the bulk point here is integrated on an asymptotic slice of the ADS space, but only over this Rindler wedge, or the causal diamond of the boundary. Okay, so this, if you like, is just a sort of trick or a way of rewriting this boundary CFT operator in terms of the bulk HKLL operator. Of course, you could have just sort of trivially done this by just scaling out some power of z from this capital phi and sending z and taking the asymptotic limit. This just happens to be a smarter way to rewrite that. I should say that you can check this formula by simply using the fact that this retarded bulk to boundary propagator has a certain asymptotic behavior. This HKLL operator has a certain asymptotic behavior. And when you take these and you plug them into this formula and evaluate this integral on an asymptotic slice, you just end up recovering the CFT operator. Okay, but this is a sort of slightly more useful way of rewriting this expression, because now once you have a symplectic density integrated over some region, then you can push that integral into the bulk. So for example, in this figure, the original integral was on the Rindler wedge in the asymptotic boundary, but because the symplectic flux is conserved, one can just push this flux integral into the bulk, close to the horizon of the bulk Ryuta-Kainagi surface. And it turns out that the reason for doing this is that once you do that, once you push this integral into the bulk, the integral, the S integral that appears in this formula is much easier to evaluate. Okay, effectively what happens is that the S integral ends up picking a pole in this sinh squared function, which appears in the smearing function. All that happens is you end up picking up a pole from that sinh squared. And after the dust settles, you end up with this particular formula for delta K, where again, let me remind you that this capital phi is the bulk HKLL operator, and little phi is sort of the bulk, the value of the bulk field configuration that corresponds to turning on the source lambda in the CFT. Okay, and this formula is, you probably recognize, is exactly the same formula that was proposed by Mark and Nima and by JLMS for the bulk modular Hamiltonian. So that immediately implies that at least at first order in this expansion, the CFT formula for the modular Hamiltonian is indeed consistent with JLMS and this paper of Anima and Mark. And of course, you can also repeat this calculation. So sure, I presented the calculation for a scalar operator, but you can also repeat it for a stress tensor deformation. In that case, you end up reproducing not just the bulk modular Hamiltonian, but you also end up reproducing the area operator. So at least at first order, then this formula for the modular Hamiltonian correctly reproduces GLMS. But so in ongoing work right now, we are trying to generalize this to higher orders, in particular to see that this formula at second order correctly reproduces the bulk GLMS formula. And at second order, there's sort of an interesting thing, feature that one would like to observe, which is that at that order, there is a contribution from quantum extremality. So I didn't want to go into a lot of detail for this, but roughly speaking, the point is that if you try to work out the second order modular Hamiltonian from the bulk perspective, there are of course a bunch of terms coming from back reaction and bulk entanglement and so on. But there is interestingly also a contribution coming from quantum extremality. Okay, the point is that at that order, because the bulk entanglement entropy is non-trivial, that sort of back reacts on the quantum extremal surface and gives you a correction to the modular Hamiltonian, which is of, roughly speaking, of this form. It involves the bulk Anek operator, or the bulk half-sided null energy operator, integrated on the bulk horizon. And there are actually two of them with some propagator along the Ryuta-Kanagi surface. Okay, so there are some interesting contributions to the bulk modular Hamiltonian at this order coming from quantum extremality, and somehow our formula for the CFT modular Hamiltonian should already know about this physics. And so that's something we are trying to extract in ongoing work right now. And there are several other questions for future work. One interesting question, for example, is whether this formalism can also be improved to incorporate multi-trace operators. In particular, this nice paper from UBC explored the role of multi-trace operators and some pathologies in those cases. But it might be interesting to revisit multi-trace operators from our perspective. Okay, so I'm going to stop there and let you ask any questions.
Thanks for the talk. Great. People have questions, go ahead and ask them.
So I was wondering if, does this direction tie into this work you had with Aitor a while ago, kind of understanding Einstein's equations and sort of relating that to bulk, or to the equivalence between the modular flows? Can this make that more explicit? Or?
Yeah, that's a great question. Actually, that is indeed, that would also be another application of this this formalism, which is to, so in that paper, although we tried to give a general argument, there were some underlying assumptions, like we were assuming locality of modular flow very close to the entanglement cut and so on. So there were some arguments which were sort of had to be to be put in by hand. But this is a much more explicit construction. So in principle, if one could one could show that to all orders in perturbation theory, this formula that we have in the CFT just agrees with the bulk formula entirely, then there's going to be, it's going to be just a much more explicit version of that paper we wrote with Aitor.
Yeah, that seems like it would be nice.
Right. And in particular, one thing that I would try to look for is that in that paper with Aitor, I think one of the nice results was, although we didn't stress on this, but one of the nice results was that one could sort of invert that argument and show that if the bulk and boundary modular flows agree, then it must be the case that the Ryuta-Kanagi formula is true. The only way you can have equality of bulk and boundary modular flows is if Ryuta-Kanagi is valid. And so I think that would also be another thing to look for in this generalization, which is that, so a much more explicit derivation of that statement.
Actually, on a point you made there, Onkar, I think in the paper version you comment on this statement about locality of modular flow near the extremal surface.
Yes.
Do you want to comment on how that ties into your formula here? Or?
Yes. I didn't explain that here, but using this formula for the modular Hamiltonian that we have now, you can just try to see what happens to modular flow of an operator. So we have this formula for the modular Hamiltonian right here. Now imagine that you have some other operator, let's say O tilde, and you decide to modular flow O tilde with this modular Hamiltonian. And then you imagine taking O tilde very close to the entanglement cut. And you ask, well, how does this non-locality of the modular Hamiltonian affect O tilde as it goes very, very close to the entanglement cut? And what you find is that all of these contributions from the non-locality of the modular flow are highly suppressed when the operator tilde goes to the entanglement cut. And you can show this very explicitly. So we have a section in our paper where we try to do this at some order, but it's clear that this is going to work at any order. So that's right. So you can use this formula to show that modular flow becomes local as you approach the entanglement cut.
Okay, thanks.
Did you have any more thoughts on the role multi-trace operators might play in this story?
Yeah, that's a very good question. Unfortunately, I don't, because we sort of heavily relied on the fact that we were turning on a local operator. And many of these calculations just break down when you have a bilocal or a multi-local operators, just like you guys already pointed out in your paper. The only thought I had was that in some special situations, and I have to say again that this is not the general story, in some very special situations, you can do the following. You can imagine, so say you had a deformation with a bilocal operator. You can imagine doing the OPE of those two operators and writing that as a sum of local operators. And then once you have a local operator which is turned on, then all of these calculations work. Now here, I'm just sweeping all of the subtlety of your paper in the statement that the OPE converges. In some special situations that you can engineer, this OPE does converge and this works. But your paper is the more general story where the OPE doesn't converge, and then I don't know what to do.
Okay. Does anyone else have any questions? Great, let's thank Onkar again.
Thank you so much.
Thanks. Yeah, this was a nice paper.
Thank you so much, Mark. Yeah, I really wish I could. I hope that I can visit UBC at some point once this whole thing settles down.
Yeah, that would be great.
Yeah.